Hello! In our last mechanics video, I showed you how to calculate the tension force caused when a spring or elastic string is stretched, and also how to calculate the thrust force when a spring is compressed. But today, we're going to take that one step further and show you how to use these calculations in the context of a wider, bigger problem. Okay, let's get started. So, one of the first queries we might have is when are we meant to know to use forces to solve problems involving elastic strings and springs? Well, crucially, you're looking out for the following scenarios. The first of which is if you're dealing with a situation that involves the object or system as a whole being in equilibrium. The reason that's important is because that's telling us the acceleration in the situation is equal to 0, and a handy equation that involves acceleration is F equals ma, which therefore implies that we need to use forces. However, the question could be worded in a slightly different way. Instead, the question could be asking about a situation that involves a particle reaching a maximum velocity. The reason that is again going to be a forces situation is if something reaches its maximum velocity, then you know the acceleration must be equal to 0 at that point, and again, if a is equal to 0, we know we could be using F equals ma. And these are the two main scenarios. However, there is a third type of wording you do have to watch out for, and that is the word resting. And I'm being very picky with the wording there. I'm being very specific by saying it's only when it says resting that it implies the object's in equilibrium. By saying resting, it's not the fact it's saying rest that means we know it's at equilibrium. By saying resting, it's implying that it's at rest now and it's going to be at rest in the future, which means that the velocity isn't changing, which implies the acceleration is equal to 0, which means it's in equilibrium. So that's something very specific to watch out for. Do watch out though, if it says at rest, that does not mean equilibrium. So, very small distinction between those two things, but it does make a difference. Anyway, let's put that into practice with a first example. So, we've got a particle of mass 2 kilograms being dropped onto a light spring that's been placed vertically. So, just trying to draw a little picture to visualize what's going on, we've got a particle that's falling onto a spring. So, therefore, obviously, the particle's going to land on the spring, and then the spring's going to basically compress when the particle lands on it. So that's what is going on, but then reading on further, we've got the natural length of the spring is 0.4 meters, so we know L equals 0.4. It's got a modulus of elasticity of 156.8. Wow, okay, so let's write that down. That's what lambda would be. And we want to find the length of the spring at the moment when the particle reaches its maximum speed. And do watch out, that does say speed rather than velocity, but remember speed is just velocity without direction. So this is one of the scenarios we were talking about before effectively, and therefore that's why we know, okay, we're going to want to use forces to solve this problem. So therefore, drawing a force diagram, we've got our 2 kilogram object, and therefore if we've got the 2 kilogram particle, we know it's got a weight of 2g. But then, as the particle falls, it's compressing the spring, which means the spring is going to be pushing back with a thrust force going up. So, that's what's going on, but as it reaches its maximum speed, therefore we know A is equal to 0. So therefore, putting this into an F equals ma, we've got T minus 2g is equal to the mass times by 0, which is 0. Cool, then we can start using the equation for thrust. So therefore that would be our lambda, 156.8, lots of our compression, x, divided by the natural length of 0.4. And we've ultimately just got to solve this equation. So of course moving stuff onto the other side as is relevant. I can then times both sides by 0.4. And then we can divide both sides by 156.8. And if we type that into our calculator, we will get 0.05. However, watch out, this isn't the final answer to this question because they wanted the length of the spring at the moment when the particle reaches its maximum speed. X is not the length of the spring, it's just the amount the spring has been compressed by. So therefore, if we want to work out the length of the spring as a whole, it's going to be its original length minus the amount we're compressing it by. So therefore the final answer is 0.35 meters. Remember units, it's always important, but we've done example 1. And with that out of the way, there's more information I want to tell you about in this video, which is that you sometimes have to deal with situations when a particle has been attached not to one of the ends of the string or spring, but somewhere along the actual length of the spring, somewhere in the middle, not directly perfectly in the middle, but just not at either end. So when this sort of situation happens, it's often a good idea to split the string up into 2 separate pieces. One piece on one side of where the particle has been attached and the other piece for the other side of where the particle has been attached. This means that you can then do the tension or thrust calculations separately for the 2 separate pieces, but good news, although you're having to do 2 separate calculations, the modulus of elasticity for both of those pieces of the original string or spring are going to be the same as the original string. So therefore, that actually means it's not as bad as it first looks. However, I should note that it is still possible to treat the string or spring as one big object if the particle has been placed specifically at the midpoint and the string or spring has been stretched by the same amount either side of the particle. So in those situations, it's up to you whether you want to split it up into 2 separate objects or treat it as one big thing, but personally I always split it up just so I don't have to worry about this distinction. Cool, let's have a look at a second example that uses this fact. So we've got a light inextensible string of natural length 4 meters. That means straight away we know that the value of L is 4. It's attached to 2 points A and B, which are the same height as each other and 4 meters apart. So let's start doing a diagram to help us visualize what's going on. So we've got A and B, and these are 4 meters apart from each other. Then a particle of mass m kilograms is attached to the midpoint of the string. Now, because the particle's got a mass, it'll have weight. The weight force will be pulling the particle down, which will happen because the string is elastic, so it will stretch. So therefore, what sort of situation we're going to end up with is a situation where the string is going to stretch downwards, and it's going to keep on stretching until the weight of the particle, which will be the mass m times by g, is being balanced out by the tension in the string. And the tension will manifest itself as 2 tension forces, one in each half of the string. And that is true regardless of whether you want to treat the string as 2 separate strings, which was the initial advice I gave, or if you want to treat the string as one big string, because that is possible here because the mass has been placed at the midpoint of the string, meaning it's going to stretch it in an even manner. But funny enough, that is also one of the reasons I don't like treating the string as one big thing, because of the fact that can lead to some confusion about whether you need both tension forces or not. So we are going to treat it as 2 separate ones. Anyway, reading on, the system is left with the particle resting in an equilibrium position. So what is this telling us? It's telling us that A equals 0 and that we want to use forces to solve this problem so that we can use that fact that A is equal to 0. The string has a modulus of elasticity of 9g newtons, so therefore lambda is equal to 9g. Remember in mechanics, in maths A level, g is equal to 9.8. And this makes an angle of 40 degrees with AB. So we know the string is making this angle of 40 degrees here and also here, because again, we know it's going to be symmetrical due to the position of where the mass was attached to the string, the midpoint. Cool, so we have extracted all the important information. We want to find what m is as a value now. Well, in order to do that, let's start by doing forces. So I'm going to take upwards as my positive direction. And of course, we've got a problem because tension is not happening directly up, it's happening diagonally. So we need to resolve it using a right angle triangle. That's going to be quite easy to do. It's just going to be t sine 40. Of course, though, we've got 2 tension forces, and they both are resolved to be t sine 40. So I could just add another t sine 40 on if I wanted, but it's just easy to double it. And then we've got the weight going down, so that's minus mg, and that's going to equal 0, because the mass times the acceleration will be 0, because the acceleration is 0. So that's our F equals ma done. G's not an unknown, of course, but M and T are, and so therefore we're going to want to do something about that, and the easiest thing to start with is to use the formula for tension, as we're of course dealing with an elastic string. So therefore T is equal to lambda x over L, but at this stage I'm going to want to take account of the fact that I am going to split the big string up into two mini strings. So therefore, as I'm going to be splitting the string into half, that means the natural length of the two mini strings is each going to be 2. And therefore I'm going to call x the extension in each of those mini strings. So therefore, as a result, we are going to have the tension being the lambda, which is 9g. As I said before, the modulus of elasticity will carry over to both parts of the bigger string as well, so that's why I'm still allowed to use that. But then the extension, which we don't know, so I'm going to put it as x, and then we've got the 2 for the natural length. So that's our lambda x over L. And we're still multiplying that by the 2 out the front that we've got, and the sine 40 degrees, and then I'm still taking away mg. We could then simplify that left-hand side a bit, so therefore we end up with 9gx sine 40 degrees minus mg equals 0. We could then also move the mg over to the other side and cancel out a g on both sides. So if we do that, we'll end up with 9x sine 40 degrees is equal to m. Cool! However, in order to find m, we now need to find what x is, and to do that, we're going to need to look at what's going on visually, again with the scenario. We had the string being stretched downwards like this, and then we have that we know that this length horizontally originally was 4. However, that means we know that each half is 2 meters here and here. That's important because it means we also know that this bit diagonally is going to be the natural length of that half of the string, which was just 2, plus the amount we're extending just that little bit of the string, because remember I defined x as just the amount we're extending each half of the string. So therefore that's important when we combine it with the fact that we know this angle is 40 degrees, because we can do a bit of trigonometry. We know the hypotenuse, which is x plus 2 or 2 plus x, times by cosine of 40 degrees is equal to the adjacent. So therefore, that's going to equal 2. So that means we can rearrange that to get what x is in terms of some numbers. So I could divide both sides by cos 40. So doing that, we have this, and then we take away 2. And although that isn't a very nice number, it is the value of x in exact form. So all I've got to do now is plug that into my equation up here. So we've got 9 lots of 2 over cos 40 degrees minus 2 lots of sine 40 degrees is equal to m. And if you type that all into the calculator, you will get m is equal to 3.5336, etc., which means that m is equal to 3.53 kilograms to 3 significant figures, because g ended up cancelling out as part of the calculation, so that's why we don't need to restrict it to 2 significant figures. And so we're done. Hopefully you found this video useful to help you know when you're meant to be using forces with elastic strings to help you deal with certain situations, but also how to calculate elastic tension if it isn't one of those standard just stretch from either end style of problems. Okay, see you in a future video, because we've got more stuff to talk about elastic strings and springs in the future as well. Goodbye!